What you're looking at here is a full drone photogrammetry workflow, starting with a set of overlapping aerial images captured during a drone mapping flight. Rather than simply viewing these as individual photographs, the software uses them as raw spatial data to reconstruct the site in 3 dimensions and generate a measurable mapping output. This is essentially where the workflow begins, a collection of overlapping images that will be processed into something far more useful than just aerial photography. The first processing stage is photo alignment. At this point, the software analyses every overlapping image and starts calculating the exact camera positions in 3-dimensional space. This is where it begins understanding how all of these individual photographs relate to one another. During this stage, the software is effectively comparing image overlap, recognizing common features and building the geometric foundation for the reconstruction. The result is an initial sparse point cloud. This shows the calculated camera positions and the early geometric structure of the site. It's not yet a finished model, but it's a framework the rest of the workflow builds from. At this stage, manual reference markers can be added and checked across multiple images. These tie points help the software recognize the same physical location from different camera angles. That improves consistency throughout the model and gives greater control over the reconstruction. Each marker needs to be checked and positioned accurately across the image set so that the software knows it's referencing the exact same point every time. Once those markers have been added, the project can be rebuilt using that additional reference information. This helps tighten up the reconstruction and improves confidence in the overall model. This creates a much more detailed digital representation of terrain, structures and surface geometry. The next stage generates a dense point cloud. Instead of a basic geometric framework, the software now builds millions of individual spatial points across the site. At this stage, we're moving from rough geometry into real spatial detail. From there, that point cloud is converted into a polygon mesh. This creates an actual 3D surface made up of connected geometry. This is essentially the structural framework of the reconstruction. Millions of faces and vertices combine to build a full digital surface of the site. At this point, the site now has physical shape and structure, but it still hasn't had photographic detail applied. At this stage, we're looking at geometry rather than photographic realism. The next stage is texture generation. Here, the software takes original drone imagery and projects it back onto that 3D mesh. This is what transforms raw geometry into a visually realistic model. Once complete, we get a fully textured digital reconstruction of the site. What you're seeing here is real photographic data wrapped over the 3D surface geometry. This gives a much more intuitive visual understanding of the site and allows it to be explored from angles that simply aren't possible from the ground. A georeferenced orthomosaic is then generated. This creates a distortion-corrected top-down map built in a measurable coordinate system. Unlike a normal aerial photograph, this output is designed for practical measurement and analysis. This is the Orthomosaic output. A high detail measurable map of the site generated from the processed image data. Because perspective distortion has been removed, this can be used much more effectively for planning, inspection work and general site visibility. Measurements can also be taken directly within the output. Distances, boundaries and site features can all be checked from within the processed map itself. That moves the workflow beyond simple imagery and into something far more practical. A digital elevation model can then be built from the processed point cloud. This introduces terrain intelligence by analysing height data across the site. This allows us to visualise height variations, surface gradients and elevation change across the land. Outputs like this can be particularly useful when understanding terrain behaviour and land conditions. The end result is a combination of visual and measurable outputs created from a single drone survey. From 3D models and orthomosaics through to measurements and elevation data. This kind of workflow can support inspections, planning, progress tracking and overall site visibility. It's not just aerial imagery, it's usable site intelligence from the air.